Okay guys, so what I'm going to just do here is record a short video demonstrating how to run an independent groups t-test using SPSS. So what you can see here on my screen is I have got an SPSS data file, a .sav file open. It's got data on a number of variables, and it's got a participant ID, it's got a scale variable for a participant's weight, a scale variable for their height, a scale variable for their age, and also a categorical for sex, which are they're coded 0 and 1, and if I toggle between the two, you can see there 0 is male, 1 is female. So what I'm going to do in this particular video is just demonstrate how to with a couple of examples how to run an independent groups t-test. So to do that, what I'm going to do is going to click on analyze, compare means and proportions, and what I'm going to select is this independent samples t-test. That's the option you want in SPSS. And what I'm going to do is look to see if there's a difference between males and females, so the categorical variable sex with 2 levels in terms of weight, and then I'll repeat a similar analysis of looking at height to illustrate a couple of things. So the test variable, the dependent variable we're interested in, outcome variable is going to be weight, and obviously our grouping variable is sex. So if I pop that into group, it moves sex over into the grouping variable box there. If I click define groups, by default SPSS has populated it with the numbers 1 and 2. I'm going to change these. This can be helpful, but in this case we know that the sexes, the categories have been dummy coded 0 and 1, so we want to change those to 0 and 1 in this particular case, and click continue, and you notice here there's a little tick here. I can take that off, put it back on, and that will give us a number of different estimates of effect size. So if we get a significant difference, statistically significant difference, we might want to know what the practical significance of that is. So it'll give us a couple. The one we'll probably look at is Cohen's D in this particular case. So having set that up, all I need to do now is click OK, and what we'll see is we get the output window pops up. So with SPSS, as you know, you have your .sav file, which is the data file, and the output appears in a separate window, usually a .spv file when you save them. So what we've got here for this first analysis is giving us 3 tables. The first one is a table of descriptive statistics, and you can see here we've got our categories, male and female, 22 males, 28 females in this data set, and the mean weight for males is 76.92 if you round that to 2 places, and the mean weight for females is 61.65. So weight for males higher than females in this case, but what we're interested in is it's statistically significantly higher. Something else that's worth looking at here is standard deviation. We can see we've got a standard deviation for the weights for males of 11.55 and for females of about 7.60, so they're a little bit different. So that's probably going to be relevant in a second when we look at tests for equality of variances, or Levene's test for homogeneity of variance. So the second table we've got here is our independent samples test table, and that gives us the result of our t-test. But the first two, SPSS combines a couple of tables here essentially. It gives us the output of 2 different tests. First, the Levene's test, which appears in these first 2 columns. It gives an F ratio and a significance. And you can see they're headed, they're labelled there, Levene's test for equality of variances. And then it also gives us our t-test and significance levels. So the first thing we want to do when interpreting the results of this test is look at the output for Levene's test, because it tells us which of these 2 rows, whether or not we can assume equal variances for our data set, and which of these two t-tests, equal variances assumed or equal variances not assumed, we should interpret. In this case, so the Levene's test, it's effectively given us an F value, an ANOVA test, and it's given us an associated significance. And this is a pre-test, so it's a test to assess whether the data we are using for this analysis meets the assumptions of a parametric statistical test, and in terms of each of the groups having roughly equal variance about their group mean. And what we can see here is we've got a Levene's test statistic of F of 6.22 if we round that to 2 places, and a significance level of P is equal to 0.016. So at the 0.05 alpha significance level, what we've got here is a statistically significant Levene's test. And when it's statistically significant, that means it means we can't assume equal variances between the groups. There's the possibility, but the variances are unequal, and that's going to affect the results of our test. We're not meeting the assumption of homogeneous variance that's necessary for this type of parametric statistical test. But luckily, SPSS is kind to us. It gives us like two options in terms of two different t-tests that we can interpret. So the first row here, equal variance is assumed, gives us a t-test value, and the second, equal variance is not assumed, also gives us another t-test value. We know because Levene's is significant, we can't assume equal variances. So the row we need to use is this equal variances not assumed row just here. And you see from that we get a t-value of 5.35. And if we use a two-sided significance level, because we didn't necessarily make a prediction that one group would be higher than the other, we didn't make a directional prediction, we get a p-value of less than, p is less than 0.001. So we're getting a statistically significant t-test, indicating there is a statistically significant difference between the weights of males and females. Okay, and to interpret like what that difference is, because we've only got two groups, we can just look at this table of means here, the descriptive statistics. So we know the difference in weight between males and females is statistically significant, and we know that males have are heavier than females in this case. So statistically significantly higher weight in males than females. So if these two t-tests that we've used here, given that we've got a Levene's test that's significant, what you'll notice is the first t-test, where if we could have assumed equal variances, it's been created using degrees of freedom of 48, whereas the second, where we couldn't assume equal variances, got much lower degrees of freedom, 34.61 if we round that to two places. So to work out the t-value when we can't assume equal variances, the degrees of freedom have been reduced to make the test a little bit stricter, so we're not making some sort of type 1 error or getting erroneous results. Okay, so we know we've got a statistically significant difference between males and females in terms of weight. Males are heavier. Does that equate to a practical significance? Well, one way you can look at that is looking at measures of effect size, and we're just going to look at Cohen's d here. We've got a table that's given us three: Cohen's d, Hedges correction, Glass's delta. There may be different situations in which you'd prefer one over the other. I'm just going to interpret Cohen's d here. If we look at Cohen's d, what we're interested in is the point estimate here, and we get a value of 1.601. So there are different rules of thumb as to what constitutes a large effect size, what constitutes a medium, what constitutes a small effect size. So 1.6 for Cohen's d would be an extremely large effect size. So a very practically significant difference between males and females in terms of their mean weight for this particular sample. Okay, so in terms of these kind of rough guidelines, rules of thumb for what constitutes a different sized effect, they're easy enough to Google and look up. But what I will do just before finishing is I'll kind of run a second t-test here. We'll run it with a different dependent variable. So we'll use the same data set. I'm going to go analyze, compare means, independent samples t-test. But this time what I'll do is I'll remove weight from the test variable and we'll use height instead. It's just to illustrate the difference in terms of the Levene's test that I'm doing this really. So the test's already set up, so if we just click OK, what we get again is table of descriptives, our table with our t-test and Levene's test and our effect size. So same numbers of males and females, it's the same data set. We're seeing in terms of height, mean height for males 175.84, for females 164.65. So males are taller than females. If we look at the standard deviation in this case though, we've got a standard deviation of roughly 7.48 for males and 6.32 for females. So they're not massively different in terms of how much variability there is about the group means in this case. And that's kind of relevant when we look at our second table. So first of all, we're going to interpret Levene's test, and this time we can see for the height variable, we've got an F value of 0.71 and a significance for Levene's test of 0.404. So a non-significant Levene's test in this case. So what that's telling us, we probably, the fact that it's non-significant is telling us we probably are safe to assume equal variances between the two groups. So we can, to interpret our t-test, we could use this top row on this occasion, where equal variances can be assumed. And when we do that, we see we've got a t-value of 5.73, and if we use the two-sided p again, we've got a p significance level of p is less than 0.001, so we've got a statistically significant difference in height between males and females. To interpret that, put that in context, we can just look at the group means. What that's telling us is males are statistically significantly taller than females for this particular sample that we've got. Does that equate to a practical significance? Well, we can look at Cohen's d again, we can look at our measure of effect size, and we see we've got a similar point estimate for Cohen's d as to the previous analysis of 1.634. So what that's telling us is it represents a very large effect size. So we've got a statistically significant difference between height in terms of males and females, and that is practically significant as well. So males are the mean height for males is significantly higher than it is for females. Okay, so that's it. That's independent groups, independent samples t-test, and one where we couldn't assume equal variances and one where we could. Thanks for listening.